Hi, welcome to my channel. In today's video, I want to talk about semiconductor detectors. So these are solid state detectors that can detect nuclear particles like alpha particles, gamma radiation, but they are made out of semiconductor material. So before I talk about the principle and working mechanism of this kind of a detector, first let's talk about what is a semiconductor. So semiconductor is a material that we can distinguish from insulators and conductors by saying that they have an intermediate band gap. What does that mean? So usually materials are made out of atoms and molecules which form some kind of a crystal structure, and the electrons in the outermost layers of these atoms are either free to move around or they are bound to the atom. So if the electrons are bound to the atom, that means they are not free to move around and they do not help in the conduction of electricity. However, if the electrons are free to move around, then that kind of a material helps in conduction of electricity. Now these two kinds of electrons can be distinguished by looking at their energy levels because they form what is known as bands. So there are two kinds of bands which we need to know. One is the valence band, the other is the conduction band. So if an electron is in a valence band, it simply means that the electron is bound to the atom, it's not free to move around, and it does not conduct electricity. If however the electron is in the conduction band, it means that it is not bound, it's free to move around inside the material and it will conduct electricity. Insulators are distinguished by the feature that the gap between the valence band and the conduction band, which is also known as band gap or forbidden gap, this kind of a gap in an insulator is very high, so high that the electrons in the valence band does not have sufficient energy to jump to a conduction band, and therefore that kind of a material does not conduct electricity. On the other end of the spectrum, you have metals or conductors where the valence band and the conduction band are very near or they even overlap. In such a case, the electrons in the valence band can easily jump to the conduction band, thus they are very good conductors. Now in the intermediate region, you have something called semiconductors. So in semiconductors, the valence band and the conduction band are separated. However, the separation is very small, so that even due to thermal excitation, the electron in a valence band can jump to a conduction band. So the electron can jump from a valence band to a conduction band due to thermal excitation. In those cases, those materials are known as semiconductors. So semiconductors have a band gap which is somewhere intermediate compared to a very large band gap in insulators and extremely small band gap in conductors. Now semiconductor detectors are made out of these kind of semiconductor material. So in this case we have a PN junction diode. So a PN junction diode is made out of an N-type semiconductor and a P-type semiconductor. Now what are N-type and P-type semiconductors? So they are made out of the same material but they have different kinds of doping, because of which the majority charge carrier is different. So in an N-type semiconductor, the majority charge carriers are electrons, while in the P-type semiconductor, the majority charge carriers are holes. Now what are holes? Now I told you that whenever there is sufficient amount of energy due to thermal excitation, the electrons in the valence band can jump to the conduction band. So when an electron jumps from a valence band to a conduction band, then it leaves in its place a vacancy. This vacancy acts as a positive charge carrier and it is known as a hole. So hole is the vacancy left behind when an electron jumps from a valence band to a conduction band. So the electron in the conduction band is a negative charge carrier and the hole in the valence band is a positive charge carrier. So N-type and P-type semiconductors are distinguished by the feature that even though they are made out of the same material, like let's suppose silicon, they have different doping, because of which the majority charge carriers are different. So in N-type semiconductors, the electrons in the conduction band are the majority charge carriers, and in P-type semiconductors, the holes in the valence band are the majority charge carriers. So the way this kind of a device can be created is you have one layer of P-type semiconductor and another layer of N-type semiconductor. Now this kind of a device is known as a PN junction diode. Now in a PN junction diode, there is something called depletion region. So what happens is that along the junction between the P-type material and the N-type material, what happens is that the majority charge carriers in the N-type are electrons, they can diffuse in the P-type, and the holes are the majority charge carriers in P-type, they can diffuse in the N-type. So when the opposite charges diffuse inside each other, then they basically recombine in a very small region and they basically create what is known as a depletion region. So depletion region is that that particular region in which the electrons from the n-type and the holes from the p-type diffuse and recombine to create a sort of a neutral region. So there is no charge carrier in this depletion region. Neither there are free electrons in the conduction band, neither there are holes in the valence band in this particular depletion region. It is free from any kind of a charge carrier. Now it is this depletion layer that behaves as a nuclear detector. So to create a large depletion layer, we create a reverse bias scenario. So what is a reverse bias? We connect the PN junction diode to some kind of external voltage. However, the negative terminal of the battery is connected to the p-type and the positive terminal of the battery is connected to the n-type. So the p-type has positive charge carriers, but it is connected to the negative terminal of the battery. N-type has electrons as majority charge carriers, but they are connected to the positive terminal of the battery. This is known as a reverse bias configuration, and in the reverse bias configuration, the current is minimal in the circuit. So because of opposite polarities, the charge carriers are attracted in opposite directions and you end up creating a larger depletion region. So why is a reverse bias scenario important? First of all, in reverse bias scenario, you have minimum amount of current flowing through the circuit, which is necessary because the only current we want in the circuit should be associated with the existence of some kind of an external nuclear particle. And the second reason is that in reverse bias, we have a larger depletion region, which is important because it is the depletion layer which acts as a nuclear detector. So to understand how this setup works as a nuclear detector, let's look at this particular diagram. So a PN junction diode is connected in reverse bias to an external battery and a load resistance. So there is some sort of electronics associated with the load resistance which is capable of detecting the potential drop across RL and also the current pulse associated with it. In reverse bias configuration, there is a minimum amount of current flowing through the circuit. However, what is going to happen if an external nuclear particle enters the depletion layer? So let's suppose an external nuclear particle like an alpha particle enters the depletion layer, then the effect of this is going to be that it leads to the creation of electron hole pairs. So when an external alpha particle enters the depletion layer, it basically collides with the atoms and molecules in that region and transfers energy. Now the electrons in the valence band of that particular depletion layer will absorb that energy and jump to the conduction band. When that happens, we end up getting a free electron and a hole. So the effect of the existence of an external alpha particle inside the depletion layer is the creation of an electron hole pair inside the depletion layer. So an alpha particle can create an electron as well as a hole pair inside the depletion layer. However, the number of electron hole pairs created are extremely huge because the alpha particles can have energies ranging from around 4 to 9 mega electron volt. However, the amount of energy necessary to make an electron hole pair in a semiconductor kind of detector like this is somewhere around 3 electron volt. So as you can see, the alpha particle has almost million times greater energy than it is necessary to create an electron hole pair. That means one alpha particle with large number of collisions can lead to the creation of millions of electrons and holes in the depletion layer. So when an alpha particle or a gamma radiation or some other nuclear particle enters this depletion layer and creates a large number of electron hole pairs, then these electrons basically move through the circuit and then they lead to the effect of a potential drop across RL, which is detected through some kind of an electronics associated here as some kind of a current pulse. And the existence of a current pulse across RL is proof of the existence of an external alpha particle inside the depletion layer. So this is the most simplest way in which this detector works. An external nuclear particle enters the depletion layer and transfers energy to the depletion layer and leads to the creation of a large number of electron hole pairs. These electrons complete the circuit and is detected as some kind of a current pulse associated with the load resistance. So in the last two videos, I talked about ionization chambers, proportional counters and Geiger-Müller counters. So they had a similar kind of a configuration, but instead of a semiconductor device, they had a gas chamber. So there was a gas chamber which was connected to a similar setup. So when an external alpha particle enters the gas chamber, due to ionization, it created ions and electrons. And these electrons and ions were attracted to opposite polarities and they ended up creating a current pulse, which gave us proof of the existence of an external nuclear particle. So we have a similar situation happening here, but instead of an external alpha particle creating a free electron and an ion, in this case, an external alpha particle creates an electron hole pair. However, if I make a comparison between gas detectors, that means gas-filled nuclear detectors, and semiconductor detectors, there is a very important distinction. For example, the amount of energy needed to create an electron hole pair is somewhere around 3 electron volt. However, in the case of gas detectors, the amount of energy needed to create an electron ion pair was somewhere around 35 electron volts. So as you can see, the amount of energy necessary to create an electron in the depletion layer is almost 10 times less in a semiconductor device as compared to the amount of energy necessary to create an electron in a gas detector. That means the same external alpha particle can create 10 times more electron pairs in a semiconductor device as it creates in a gas detector. That means the amount of current pulse associated with the number of electrons is 10 times greater in the case of a semiconductor detector as opposed to a gas detector. So because of this reason, semiconductor detectors are much better than gas detectors because the amount of current pulse is quite high, because of which there are certain advantages. First of all, this kind of a detector can be used for detection of even low energetic particles. Second of all, this kind of a detector has better energy resolution. How so? You see, the current pulse gives us an idea about the energy of the incident particle. Yes, if the energy of the incident particle is greater is the number of electron hole pairs and greater is the amount of current pulse associated with that signal. If the energy of the incident particle is lower is the number of electrons and lower is the current size. So by comparing two different current signals, by looking at their sizes, we can get an idea about the energy of the incident particles. So bigger current pulse means a greater energetic particle, lower current pulse means a lower energetic particle. Now since the current pulse associated with a semiconductor device is almost 10 times greater, therefore this kind of a device has a better resolution. That means it is easily able to distinguish between two nearly lying incident particles having very close energies. Also, there is the obvious benefit of a semiconductor device being very small and compact. Gas detectors are quite large compared to semiconductor detectors, which can be made from extremely small, thin films. So that is the general working principle of a semiconductor detector. So you have a PN junction diode in reverse bias configuration, which has a depletion layer. If an external alpha particle comes inside the depletion layer, it transfers energy to the material by creating a large number of electron hole pairs. These electrons complete the circuit and lead to the detection of a current pulse across the load resistance. The size of the current pulse gives us an idea about the energy of the incident particle. We can distinguish between two particles having different energies by looking at the different kinds of sizes of current pulse created here. So that is all for today. I hope you have understood something about the way these kind of detectors work. That's all for today. Thank you very much.